There is a mysterious world where nothing appears to be what we consider normal. Everything that exists here is fundamental to our understanding of the physical world around us. Common sense, in this place, does not exist. This world challenges our views regarding how the universe works and our perception of reality. Everything that we currently experience with our own eyes could actually be different to what we perceive as truth. Where and what is this place? In fact, it is everywhere around us. Welcome to the world of quantum physics.
So quantum theory is essentially the theory of how things behave at very small length scales. So it's a theory that tells us how to treat very tiny particles. Essentially, if you were to boil down quantum physics into two essential results, what you would say is that it is a theory which treats particles as waves, and it's a theory which is probabilistic, which means we don't know the outcome of an individual measurement, but we can compute the probability of measuring a certain result.
Quantum physics really shows up and becomes important when you're dealing with very tiny things like individual atoms or subatomic particles. Subatomic particles behave in a very different way to large objects like billiard balls. If you have billiard balls colliding, it's pretty clear what's sort of going to happen. But when you get individual electrons colliding, it's a completely different ballpark because the world of the very small is permeated throughout with uncertainty. And so when you're dealing with the tiny objects, then it's a totally different kind of physics. You're dealing with probabilities, you're dealing with uncertainties, rather than something which is very deterministic.
Everything that exists in the entire universe, including ourselves, is made up of small particles called atoms. Atoms, electrons and light particles called photons behave very differently from the larger objects that we experience every day of our lives. For example, if I shot a pool ball towards the pool table cushion with a cue, I could predict where the ball would go, depending on the angle and velocity of my shot. The result of the ball's destination would depend upon the laws of physics, which makes perfect common sense. However, if this pool ball were an atom, the results would be completely different. The ball would not move from A to B as it would on a pool table. The ball would move in ways which completely undermine our perception of common sense. The ball would simply disappear and reappear from one place to another, completely randomly. This is called a quantum jump. As we can see, this behavior does not make sense. How can an object jump from one place to another without being anywhere in between? This is a mystery. Why do these particles behave this way? And how can this behavior possibly make sense? Atoms are tiny pieces of matter invisible to the human eye. They are the basic building blocks of all physical objects. This includes ourselves and all other life forms. Can the behavior of atoms, through quantum physics, prove that there may be a different concept of reality? How can we be totally sure that the reality we are currently experiencing is the whole truth? Are our experiences of the world around us the true reality, or are our brains creating illusions which enable us to live in an environment that we understand?
Quantum mechanics is necessary to draw upon if you're dealing with very tiny objects like individual electrons. So you might think, well, okay, I don't deal with individual electrons. I deal with, big objects. Okay, so quantum mechanics doesn't really affect me in my normal everyday life. That's not true at all. That's not true at all. Because everything is made up of atoms, all right? So you've got a nucleus and you've got electrons on the outside, okay? If you regarded that as a miniature solar system, planets, the electrons going around the sun, the nucleus, okay? Because the electrons are electrically charged, as they go round, they ought to be losing energy and gradually spiral into the nucleus. In other words, all atoms ought to collapse in on themselves. So this all really ought to collapse, but it's not. Now why is that? It's because quantum mechanics tells us that the electron, as it's going around the nucleus, is not behaving like a tiny little planet. It's behaving like a wave. It's a trapped wave. Now, trapped waves behave very peculiarly. If you've got a violin string or a guitar string and you pluck it, you only get certain notes coming from it, because only certain modes of vibration are allowed for a particular length of string and under a particular tension. And so the same applies to the electron in the atom. Only certain motions are allowed to it. It's not allowed to gradually spiral into the nucleus. And so the sheer stability of atoms and the fact that we don't all suddenly collapse on ourselves is down to the fact that electrons have this quantum mechanical wave nature. So the behavior of what the tiny electrons is doing on the very small scale does affect what's happening up here on the big scale.
Some physicists believe that there is a mathematical and reasonable explanation to the behavior of atoms. They believe that the particles are briefly skipping through other universes during the quantum jump. If this theory is true, could our universe be just one of many parallel universes of which we are unaware? Other than the theory of new universes, there is an even newer theory which attempts to explain how the universe works. This is string theory. It seems that we may not completely understand how our universe works. The universe could be different to our conception.
String theory is a theory which suggests that all the fundamental particles that we observe, all the electrons, protons, neutrons, are actually made up of tiny strings of energy which are vibrating. And the confusing thing is that these strings exist not just in 3 dimensions, but can exist in many dimensions, up to, say, 24 dimensions. And these dimensions are so tiny that they're actually not perceptible to us. We're used to walking around in 3 dimensions. But the strings themselves can vibrate in up to 24 dimensions, but the dimensions are curled up into a tiny little ball, which is many, many times smaller than anything we're able to detect. So although it's a theory which mathematically gives rise to things like why particles have mass, why we have different types of particles, it's an extremely difficult theory to test because the dimensions that these strings exist in are so tiny.
Quantum physics is far stranger than we think. The erratic behavior of atoms is just one of many things that don't make sense. Light photons also follow the rules of quantum physics. The behavior of these particles showed us this new form of physics. This was completed through various experiments. What is very puzzling, though, is that not only were photons behaving strangely, they behaved randomly across different experiments. Some experiments produced results which suggested that light is a wave, while others seem to suggest that light is a particle. How can something behave like a wave and then behave like a particle? Perhaps we don't actually understand light. What is light?
Isaac Newton thought that light was, he called it a corpuscular theory of light, little marbles or corpuscles of some sort traveling through the medium and coming out the other side like little particles. But as we'll see through history, that got modified once or twice along the way.
If you ask the question, what is light, then people used to think, well, the answer is pretty obvious. Light is a wave. We know that because Polaroid glasses, the sort that you use when you're watching a 3D film, they wouldn't work unless light was a wave. When light passes through a tiny hole in a barrier, on the other side it spreads out. It doesn't go straight on, it spreads out. Now that is called diffraction, and that is very characteristic of waves. If you're at the seaside and you've got a harbour wall, and there's a gap in the harbour wall, and the waves are coming up to that gap, you can see that they spread out on the other side. So that's another indication that light is a wave.
Okay, so light was established as being a wave for well over 200 years, and then a new experiment early on in the 20th century started to upset our understanding of what light actually was. And it's namely the photoelectric effect. It's a big name, but it's to do with photo, light, and electricity. And this is the problem. If you have a metal surface and you shine light upon it, we notice that electrons get thrown off. Experimentally, we see this happening instantaneously. It's very quickly. The minute you switch a light on, electrons start leaving the surface, and if you put a grid up here, you can actually detect the current of electrons flowing through. So far, so good. But this was the part that we couldn't understand, that if you had light of a different color, what we would expect if the wave nature of light was the only explanation for light is that perhaps it would take a little bit longer for the electrons to be ejected from the atoms on the surface of the metal. As more and more waves arrive, we might need to wait a little bit longer, but experimentally what we notice is that actually no electrons get emitted at all. And it doesn't matter how bright you made the light, if it was red or orange, no electrons were jumping off from the surface. And conversely, if you went to a shorter wavelength or a higher frequency of light, say to blue or violet, it didn't matter how weak the light was, how low the intensity of it was, electrons still jumped off from the surface. So it drives the question of what is it about violet light and red light that violet light can displace photoelectrons, but red light can't. Let me flick the switch here to change it into like a particle nature of light, the quantum theory of light. Our understanding of light was modified, and this is the theory that grew from there. That light comes down not as waves, but as particles. And if the particle of light, let's give it the name photon, comes down, it can hit an atom and release an electron from there, but it can only do that if the particle of light that comes down has enough energy. And it turns out, as we will see, that red photons, red particles of light, don't have enough energy to eject an electron, but blue ones or violet ones do, as you can see here. There comes a violet one, and it ejects the electron. And it was Albert Einstein, when he was still very young, only about 25, 26, who finally pulled all of these ideas together into a simple little equation, and that was the birth of the quantum theory of light.
How can light be both a wave, which has to be spread out because you've got to have humps and troughs, and at the same time it's a tiny, tiny, localized, a point-like particle? How can something be spread out and not spread out? And that gets you into what we call wave-particle duality, or the wave-particle paradox. And that's when all the deep thinking has to start.
If we take a close look at how we picture reality from a biological point of view, we may develop an understanding that what we think we are experiencing may not be the truth. What we see in the exterior world around us is just an idea of what reality is. When we look at an object, light enters our eyes and hits the retina. From the retina, information from the light triggers electronic impulses which travel down the nerve fibers. This information then enters a small section of the back of the brain. The signals are then processed to create a conception of reality. The human brain creates a reality tunnel. Everything that we experience is just an interpretation of an idea of reality, which is created in the mind. We can never be sure that the reality we are experiencing is the whole truth. This relates to everything: the sky, the trees, water, light, and ourselves. The reality we experience comes only from our five senses. These five senses are our vision, Hearing? Sense of smell? Taste? And touch. We may only gain an understanding of reality through these 5 senses. All our senses work exactly the same way as sight and hearing. How we process our experiences and gain an understanding of the whole world can only be derived from tiny electronic signals in our brains. Nothing else.
We can't say anything about the world when it's not being observed. You see, in the old days, it used to be thought that the job of scientists was to describe the world. All right, in order to do that, you have to look at it, you have to do experiments on it. But having done your experiments, what you actually write in a physics book is a description of the world, whether or not you're still looking at it. What you've written down there says nothing about the world as it is in itself. What you've written down there is a description of you looking at the world. You're never going to be able to say anything about a world apart from your observations of it. You had to admit that scientists have never said anything about the world as it is, and will never be able to say anything. Einstein didn't agree with that. He thought that the job of science remained what we always thought it was, which was to describe the world, not just you looking at it. And that problem was never solved. That argument started off in the 1920s, and here we are 90 years on, and nobody has solved the problem as to whether we can actually talk about the world.
Although some physicists believe that atoms, electrons, and photons might be skipping through parallel universes, which explains their strange behavior, there is, unfortunately, another issue currently confusing scientists across the world. This is the measurement problem. The measurement problem suggests that all these particles only obey the rules of quantum physics when we are not there to observe them. In short, it is apparent that quantum physics does not exist when a conscious mind is there to observe it. Atoms are invisible to the naked eye, but when we use a device to physically see them, the atoms follow the same rules of physics which we are all able to understand, in the same way that larger objects behave. Remember, everything is composed of atoms. This means that every object in the whole universe can relate to the measurement problem. If we imagine that the pool balls were atoms again, we can see that they scatter randomly from one place to another through quantum mechanics. But this behavior only exists behind our backs. The moment we look at the atoms, they behave in the same way we expect them to, according to our perceptions. The measurement problem is arguably the biggest scientific mystery of our time. Why do these particles act differently depending on whether a conscious mind is observing them or not? Could it be that our senses are creating an illusion of a world that we are able to understand?
So the question is, well, why should the observer, why should a person looking at this particle really affect how it behaves? I know some people believe that consciousness, so the actual microscopic cause of consciousness, is perhaps due to some quantum mechanical effect that we don't understand.
It appears that the atom, the basic building block of everything that exists in our world and our universe, undermines common sense. It follows another form of physics which we don't completely understand. How can a particle disappear but then reappear in another place completely randomly? Between destinations, where do they go? How can we be totally sure that anything we experience in life is the truth if we are made up of this material which undermines common sense? The biggest mystery is, why do atoms only behave how we expect particles to behave when a conscious mind is there to experience them? How can this possibly make sense? Could it be that the true reality of our physical world undermines common sense? Are our minds merely creating a different picture to the truth? If all the atoms in the universe which make up everything, the stars, Earth, water, and even ourselves, were to be separated, they would all individually look the same. So why is it, when atoms bond together to form bigger, solid objects, that they all look so different? Do all of these perceptual differences really exist? Or do they only exist in our consciousness? Is our world and everything that exists in it an illusion of the mind? Is everything that exists an illusion or reality? What is truth?